Let's talk about capillaries and capillary exchange. I'm going to give you my freeway analogy today. I want to talk about the function of capillaries and how they're like on and off ramps, how blood flow is regulated through capillaries, the types of capillaries we have, right? Not all on and off ramps are the same, how we describe the direction that fluids are moving through capillaries, and what drives that direction. We're going to do it all penguin prof style. Here we go. First of all, I want to welcome you to the freeway, right? The cardiovascular system really is like a freeway. In fact, if you took all the vessels and laid them end to end, it would be about 100,000 miles. Distance to the moon and back, or the distance around the Earth 4 times. That is an insane amount of tubes. We describe the vessels as carrying blood either toward the heart or away from the heart. Don't forget, it's the direction that matters, not whether it's oxygenated or not, okay? Arteries always carry blood away from the heart. Veins carry blood toward the heart. We have the pulmonary circuit, that's the exchange between the heart and the lungs, and we have the systemic circuit, that's the exchange between the heart and the rest of the body. These are the capillaries. They are the exchange vessels. This is where the materials get on and off the freeway. You can think about it this way, really. I mean, they're the most important part of the freeway. Do you get on a freeway and just drive around, not go anywhere, and then come back home? No, the point of the freeway is to get somewhere, to get off the freeway. So it really is all about capillary exchange. Now here, the on and off ramps are very, very small, 5 to 10 microns, but they represent 80% of the total vessel length, right? So 80,000 miles are capillaries. So they're a big deal. Okay, regulating blood flow through capillaries. You don't let all the cars on or off the freeway at the same time. Sometimes those ramps are closed. You can experience this when you're very cold, and we have surface vasoconstriction. So in order to conserve body heat, your body will shut down all of that surface flow to try and keep the heat inside the body. So what the body can do is control flow through any capillary bed by opening or closing these little pre-capillary sphincters. Okay, so sphincters are little bits of circular muscle, and when they contract, they shut down the flow through that tube. So as you can see here, if the body is not allowing blood flow through this capillary bed, it's just going to be shunted through this thoroughfare channel. So no exchange is going to be taking place. So the body controls what we call the perfusion of blood through capillaries very, very tightly. What kinds of on and off ramps do we have? Okay, we have 3 different types of capillaries. We have the first type, these are the most common. We call them continuous capillaries. They have tight junctions between the cells that make them slightly leaky, so small things can squeeze through them. Actually, even blood cells can squeeze through between the cells. They just have to go in single file. That must be so cute. Next, we have fenestrated capillaries, which have pores in them, or fenestrations. This comes from a Latin word which means window. So to defenestrate an idea is to like throw it out the window. That's such a cool word. Basically, fenestrated capillaries are permeable to larger molecules, and we find them in places like the small intestine, the kidneys, and many endocrine glands. The third type of capillary we have are called sinusoid capillaries, and these are the most holy of all. In fact, they don't even have complete basement membranes. So under the microscope, they look a bit like Swiss cheese. We find them in the liver, the spleen, the bone marrow, the lymph nodes, and some other endocrine glands. All right, directional terms. Unlike a freeway, we cannot use words like on and off or in and out because it just doesn't make any sense. So by convention, this is what we do. When we're describing the flow of materials from the blood to the cells, we call that filtration. This is a word you're familiar with because you experience filtration all the time. For example, when you are filtering pasta from water, you're pouring that material through the holes of your strainer. So we say here that the water is being filtered. When we go the other way from the cells to the blood, we call that absorption. Okay, so those are the directional terms we use. Now, the big final question is, what drives capillary exchange? In other words, what determines which way the stuff is going to move? We have 2 opposing gradients. The first one is called a hydrostatic or sometimes a hydraulic pressure gradient. If you have seen a hose, you have experienced this. If you have seen irrigation tubing, the thing is we have tubes with holes in them, and the farther along the tube you go, the lower that outward force becomes. And that's because energy is being lost to friction. So the key is, as you go along this tube, the water moving out through the holes, that pressure is reduced the farther away you get from the source of the pressure gradient. The second gradient we call osmotic pressure or colloid osmotic pressure. This is due to, drumroll please, osmosis. Okay, you know this already. If you're not familiar with osmotic gradients and osmosis, please check out this video. It basically describes how water always moves to follow a solute. So if a solute cannot move, water will move to try and kill that gradient. Okay, let's do this. From the heart, we have blood moving through arteries, into arterioles, and into capillaries, which are servicing the cells of the body. The blood will then return via venules and finally veins back to the heart. What we're trying to do is figure out what drives filtration from the blood to the cells and what drives absorption from the cells to the blood. In other words, what determines which direction the material is going to go. Gradient number 1, that hydrostatic pressure gradient. Remember, this is a filtration force from the blood to the cells that decreases along the length of the tube, right? The farther away you get from the source of the pressure, in this case the heart, the lower that outward force becomes. Remember with that irrigation tubing, that pressure decreases along the length of the tube. Okay, you got it? That's a filtration force that decreases the farther away from the heart you get. Then we have that osmotic pressure. That's the pressure from the cells to the blood that doesn't change along the length of the tube because there is always material in the blood that is not leaving. Maybe because it just isn't being filtered right now or because it's just too big to fit through the holes. So that inward or absorption direction, that force is constant along the length of the tube. Remember this one, right? The osmosis gradient, that's what we're talking about there. So now with both opposing gradients shown, I bet you can figure out what's going to happen, right? So we have an outward filtration force that decreases along the length of the tube, the inward osmotic force that is staying the same, that absorption pressure, and you just add them together. That gives you your net flow. So on the arterial end of the capillary, we have net filtration because the outward force is greater, that filtration force. And on the venule end, we have net absorption. If you want to know the numbers, and the numbers that we're talking about here in millimeters of mercury, so you just add them together. And by the way, every capillary will have one spot where the two forces are equal. And right there, no exchange takes place. You will also notice that this is not like a 50-50 split. A greater percentage of the capillary is experiencing net filtration compared to absorption. And you might think this presents a little bit of a problem. 85% of the capillary filtrate is directly returned on the venule end, right? That's not 100%. So what happens to the rest? Like, where does it go? Where it goes, nobody knows. No, we know where it goes. It's picked up by lymphatic capillaries. And that fluid is going to be examined by cells of the immune system so the body can keep track of any possible foreign invaders. As always, I hope that was helpful. Thank you so much for visiting the Penguin Prof channel. Please slam some buttons below. I'll see you in the next one. Good luck.